Good evening, everyone. Myself Gautam Sharma. I welcome you all in a Sapience Education. So today I'm going to teach you about kinetic theory of gases, where I will solve NCERT questions as per the latest syllabus 2023 and 24. So let us start question from question number one. So the question number one: estimate the fraction of the molecular volume to the actual volume occupied by the oxygen gas at STP. Take the diameter of an oxygen molecule to be 3 angstrom. See, this question has been given. Let us consider there is a cylinder and it contains an oxygen. It contains an oxygen at STP. So these are the oxygen molecules. It contains an oxygen molecules. Okay. Estimate the fraction of molecular volume to the actual volume occupied. See, actual volume occupied by this is this one. Total this volume is the actual volume occupied. Actual volume occupied. Okay. And when you see the actual volume of the gas molecules, so it will be approximately here only. It is this only. So we want the ratio of actual volume to the actual volume of the gas molecule to the actual volume occupied. This is the occupancy of the gas. So we need to find the ratio of that. Okay. So let us start doing. So first of all, volume of how you will find. So first of all, volume of one molecule of a volume of one or O2 molecule is how much? Volume of one O2 molecule. So this will be equal to 4 by 3 into pi into radius cube. Okay. So they have already given radius as equal to 3 radius is equal to 3 by 2 angstrom. 3 is the diameter, so it will be 1.5 angstrom. So we will use this to find the volume of the molecule. So volume of the molecule will be 4 by 3 into 3.14 into radius whole cube. So this will be 1.5 it will be 1.5 into 10 to the power minus 10, because 1 angstrom is equal to 10 power minus 10 whole cube. So when we calculate it, so our volume will be approximately equal to 1.41 into 10 to the power minus 29 meter cube. Okay. So this is one volume of the molecule. Now, as they are telling that the estimate the fraction molecular volume of the actual volume occupied by oxygen at STP. So at STP, number of moles will be equal to 1. So if I will take 1 mole molecule, so the volume, so I want volume of O2 molecule of 1 mole. So this will be 1 mole means what? We have to multiply it by Avogadro number. So this is equal to 6.023 into 10 to the power 23. Because in 1 mole, if you capture a gas of 1 mole, so it contains 6.023 into 10 to the power 23 molecule of the oxygen. And 1 molecule of the oxygen has a volume of 1.41 into 10 to the power minus 29. So the actual volume of the gas molecule in 1 mole of the gas is how much? This is the amount we have got, right? Now, let us find out volume of 1 mole of the gas. So volume of 1 mole of the gas. So I am not talking about the volume of the oxygen molecule. I am talking about the whatever oxygen has occupied the space at STP, that volume I want to find. So volume of 1 mole of gas is equal to 22.4 liters. So this is well known fact. So it can be also written as 2.2 2.24 and convert it into meter cube. So it will be 2.24 into 10 power minus 2 meter cube. So this we have got. Now actually they want the ratio, and this ratio is volume of 1 mole of O2 molecule divided by volume of 1 mole of O2 gas. So we have already got all the both the values. So we can find out both the value as 6.0 into 10 to the power 23 to 1.41 into 10 to the power minus 29 divided by 2.24 into 10 to the power minus 2 meter cube. So when I will calculate it, so we will get approximately value which is equal to 0.00038 or approximately is equal to 4 into 10 to the power minus 4. So this is the required result for our ratio. So if you want to find ratio, so this is our required result. I hope you have understood this question very easy. So let us do question number 12.2. So for 12.2, molar volume is the volume occupied by 1 mole of any ideal gas at a STP. Okay. So that it is 24. Basically, molar, we want molar volume. Okay. We want molar volume. So what is molar volume? Molar volume, that is the volume at STP. So we know the formula PV is equal to N, PV is equal to number of moles, that is N into RT. Now we want molar volume V such that number of mole is equal to 1. So V is equal to nRT by P. Now we want for molar, if we want molar volume, for molar volume N is equal to 1, number of mole is equal to 1. Pressure is given as 1 atmospheric pressure, so this will be 1.01 into 10 to the power 5 Pascal or Newton per meter square. And the temperature is 0 degrees Celsius, so this can be 2273 Kelvin. So for molar volume, so V molar, if we want to find, so this will be number of moles, that is equal to 1 into what is the value of R. So SI unit, if we use SI unit, the value of R is 8.314. So we can multiply it by 8.314 into temperature. So temperature is 273 Kelvin divided by pressure. So pressure is equal to 1.01 into 10 to the power 5. So when we calculate it, so what we are going to get? So if you calculate, so you will get the volume in a standard unit, that is equal to 0.0224 meter cube, and this is equal to, if we want in liters, so you can also put here 224.4 liter. So this is the V molar, and this is the standard formula. We always use this. 1 mole is will have a 22.4 liter of the volume. Okay, so I hope you have understood this question. Now let us do question number 12.3. Figure shows the volume plot between PVT versus P for a 1.200 into 10 power minus 3 kg of oxygen gas at a two different temperature. So there we have a two different temperature, that is T1 and T2, and for two different temperature, so the ratio of pressure P by T to the P is equal to like this. Okay. Now what does the dotted plot signify? So we need to find what does the dotted plot signify? So before that, we need to understand what is the ideal condition. So the ideal condition or ideal gas equation. So we know that ideal gas equation is equal to PV is equal to N into R into T. So when we put PV by T, so this is equal to NR. So for PV by T to the versus this graph, so NR is constant. It means that it behaves as ideal gas. It behaves as ideal gas. See here, dotted line represent the constant. See, this dotted line represent the constant term. So this dotted line is constant, and this only happens when the gas is ideal gas. So from here, dotted we can say here, from here we can say that the answer of A is that dotted plot signify ideal gas behavior. Ideal gas behavior. Why ideal gas behavior? Because number of moles in R will remain constant. Why? This is the only case when the gas is ideal. When the gas is not ideal, so what will happen? It may behave, it may deviate like this, it may deviate like this, it may deviate like this. So we don't know. Okay. So I hope you have understood this question very clearly. Okay. So let us go for a next question. The next question is that which is true? T1 is greater than T2 or T1 is less than T2? No, tell me. Now tell me logically, if you want that ideal gas, real gas, not ideal gas, real gas. Let us assume, not assume. We need to understand that real gas will behave. Real gas will try to behave ideally when real gas will try to behave ideally when temperature is low, and pressure is high. Okay. I think see, real gas will try to behave ideally when, see here, when you create a pressure approximately equal to 0. See here, when pressure tends to 0, so pressure tends to 0 means low pressure, but temperature should be high. So then only it will behave as an ideal gas. So here we can say that when pressure is very low, when pressure is very low, and temperature is high, then real gas behave as ideal. Now from graph we can understand that which is more ideal. This one is more ideal or T2? Definitely it is more close to the ideal gas path. So that's why this one is more ideal. It means that it should be high temperature. So the temperature T1 is greater than T2. Okay. So I hope you have understood this. Now let us go for a question number 3rd, and that is question number 3rd, and that is what the question they are asking. They are asking what is the values of PV by T where the curve meets on the y-axis. What is the value of PV by T when curve meet at y-axis? So basically, what we want P, we want PV by T, right? PV by T. Now, for an ideal gas, we know that PV is by T is equal to nR. So, what is the number of mole here? Since they have already given that mass of the gas, right? Mass of the gas, mass of the oxygen gas is 1 into 10 to the power minus 3 kg. Okay, so we can also take it as a 1 gram. So mass is 1 gram. So the number of moles is equal to mass by molecular mass. So this is equal to 1 by 32 gram. 1 by 32 grams. So we have got 1 by 32 grams. So basically we got number of moles. Now, if we got the number of moles, so can we find value of PV by T? So PV by T is equal to N into R. So number of moles is 1 by 32 into what is the value of 1 by 32 into what is the value of R? So R is equal to 8.314 joule per Kelvin. So finally, if we calculate this, so this will be approximately is equal to 0.26 joule per Kelvin. Okay. So I hope you have got this answer, right? So this is our required value of PV by T for this case only, because they have given the number of moles, because they have given mass of the oxygen gas. Okay. Now let us go for 12.3D. So 12.3D, let us read the question. If we obtain a similar plot for 1.00 into 10 power minus 3 kg of hydrogen, would we get the same value of PV by T at the point where the curves meet the y-axis? That is, we will get at this point or at this y-axis, would we get for same hydrogen? So see here. It ultimately, see, we don't have a same number of moles. If we talk about the number of moles, see here. If we talk about the value of PV by T, so this is equal to N by NR. So N is your number of moles. Okay. Now the same amount of mass, if the mass of the hydrogen gas and the mass of the oxygen gas. See, this is mass of the oxygen gas and the mass of the hydrogen gas. Okay. But we know that molecular mass of the oxygen is 32 and molecular mass of the hydrogen is 2. So the number of moles is different. What is different? Number of moles for hydrogen for same mass, number of number of moles for oxygen is not equal to number of moles of hydrogen. Therefore, the value of PV by T will differ. So you can guess that it may be that PV by T for a hydrogen may same hydrogen gas may be here, may be here, may be here. We don't know. It depends upon the situation. Okay. So I hope you have understood. Now the second part they are asking, if not, what mass of hydrogen yield the same value of PV by T? Okay. They are asking what value, what mass of the hydrogen yields same values of the P. See, we want number of moles of hydrogen for this to get the same value, to get the, this is part B question, to get the same value of PV by T, number of moles should be equal. Number of moles should be equal. As in question they are telling, that for in what mass of hydrogen yield the same amount of the value of PV by T. See, we want mass of the hydrogen. Okay, so number of mole of H2 is equal to number of mole of O2. So the number of mole of H2 is how much? Number of mole of H2 is equal to how much? So number of mole is of the H2 is equal to mass of the H2, mass of H2 divided by molecular mass of H2, and this must be equal to 1 by 32. So from here we can easily get the value. So from here mass of H2 is equal to this is equal to molecular mass of M for H2 is how much? It is 2.02. 2.02 divided by 32. So when we get the value, so this will be equal to 0.6. It will be, if you do this, you can also do it by yourself. So if you can do this 2.02 divided by 32, so this is equal approximately equal to not 0.6, so it will be approximately equal to 0.0631. So this can be written as 6.31 into 10 to the power minus 5 kg. So this amount of mass you can get, either this is gram or this is gram. So this amount of mass should be required so that the value of P by T will remain constant. I hope you have understood this 12.3 question number D. Now let us go for a question number. Let us go for a question number 12.4. An oxygen cylinder of a volume 30 liter has initial gauge pressure of 15 atmospheric pressure at a temperature of 27 degrees Celsius, and after some oxygen is withdrawn from the cylinder, the gauge pressure drops to 11 atmospheric pressure and the temperature of drop to 17 degrees Celsius. Estimate the mass of oxygen taken out in the cylinder. So let us understand the scenario. We know that if there is an oxygen cylinder here, we know we have already used the deodorant. What happens when you expel the deodorant? So what happens? Pressure decreases, and due to decrease in a pressure, so there is sudden drop in a temperature will happen. So you will feel cool while using a deodorant. So same thing happens. So what happened? It has some initial pressure P1, it has initial volume V1, and it has initial temperature T1. Okay. Now after after what happened, after there is a removal of the oxygen gas, so the third condition, second or not third condition, it is the second condition of the oxygen gas is given like this. So the second condition of the oxygen is P2, P2 and T2. What actually want? We want mass of the gas drop. So the mass of the gas is equal to what? Mass of O2, O2 withdrawn. Can we tell that change in a number of moles into molecular mass, you will get the actual mass removal. So before that, we have to put the values, what the values are there. P1 is equal to gauge pressure. So you should always remember the formula. Gauge pressure, P gauge is equal to P atmospheric pressure. P gauge is equal to not atmospheric pressure, it is approximately absolute pressure. So let us see here. Use this absolute pressure. P absolute pressure is equal to P atmospheric pressure plus gauge pressure. Okay. So from here, if you have a gauge pressure of 15 atmospheric pressure, if you have a 15 atmospheric pressure, so the pressure, absolute pressure will be equal to 1 atmospheric pressure plus 15. So this will be 16 atmospheric pressure is the absolute pressure. So the volume is 30 liter, and the temperature is, initial temperature was 27 degrees Celsius, so it can be written as 300 Kelvin. Just you convert it into the standard one. So P2 is the final pressure is approximately final pressure, it is given as 11 atmospheric pressure. So it is a gauge pressure only, right? So gauge pressure, so we have to add 1 again, 11 plus 1, so this will be 12 atmospheric pressure. So we have got 12 atmospheric pressure as a final pressure. Volume will remain same because cylinder is not changing, so volume will remain same. Temperature, so temperature is suddenly dropped to 17 degrees Celsius, so this will be how much? 290 Kelvin. Okay, so we have got these things. Now what we want change in a number of moles. So initially, first we need to find a number of moles. So a number of moles is equal to how much? So this will be P by RT. So this will be P1 V1 by R1 T1. Okay. And if we put the value, so what will be the value of P? So this is 16 into 1.01 into 10 to the power 5 into volume is 30 liter. So 30 liters, so convert it into, so 30 into 10 to the power minus 3 meter cube divided by R. So the value of R at a standard SI unit, so this will be 8.31 into the temperature will be remain 300. So when we calculate it, so we will get approximately 19.45 mole. Now we want number of moles at a second condition. So okay, at a second condition, number of mole will be equal to pressure. Same formula we use, P2 divided by R2 into T2. R2 into T2. Let us put the values. So R2 into T2. So this will be approximately equal to this will be approximately equal to 11, not 11, it is 12 into, let us rub it. So it will be 12 into volume. So volume is again 30 into 10 to the power minus 3 divided by R2 is 8.31 into 10 to the power, not 10 to the power 3, it is 10 on 8.31, and approximately it is equal to 300. In place of 300, you have to put 290. When we calculate this, so we will get the value as approximately equal to 15.09. So this we have got two number of moles of initial number of moles. This is initial condition before gas withdrawal, and this is final, that is after gas withdrawal, final condition. So change in mole is equal to 19.45 minus 15.09. So when we do this, so our value will be approximately equal to 4.36 mole. So we have got the mole. Now we can find out the mass of the oxygen withdrawn. So this we can do, mass of O2 withdrawn is equal to change in, that is number of moles into molecular mass. Why I am writing change in molecular moles? Because this amount of moles has been expelled or withdrawn only. So the number of moles is equal to 4.36 into molecular mass is 32 gram. Okay. So this if we will, this is the, if we get this, so finally we will get 139.5 gram. So we can also write 0.14 kg of the oxygen gas is expelled or withdrawn. So finally our answer is this or this. We can use both. So as per the question, we have done this. I hope you have understood this. Now let us do question number 12.5. An air bubble of volume 1 centimeter cube rises from the bottom of the lake of 40-meter deep at a temperature of 12 degrees Celsius. To what does it grow when it reaches to the surface, which is at a temperature of 35 degrees Celsius? So the condition, you need to understand what the conditions are there. So there is a water surface and there is a bubble inside the water body. And in this case, so this is, let us say this is a initial condition, initial, and after certain period, what happened? This bubble went up down. So as per the logic, you know that when bubble goes up, so what happened? Less pressure will be there. So this is our final condition. So the pressure is less, P is less here. If P is less here, so the volume of the gas will definitely, volume of the bubble will increase. Okay. So we want how much volume does it grow? What volume does it grow? So I want V2. So let us put the values initial conditions. So the volume, that is it is the one condition, it is your volume V1. So V1 is how much? 1 centimeter cube. Pressure P1. So P1 we know that P atmospheric pressure plus rho GH. Why rho GH? See, let us consider this is the height they have given as 40 meter. So at the 40-meter depth, the pressure will become P atmospheric pressure plus rho GH. Okay. Got it? And the temperature T1. So the temperature T1 they have given as 12 degrees Celsius. So convert it into Kelvin. So the Kelvin, if we convert it into the Kelvin, so the final value will be how much? 273 plus 273 plus T1, that is 35 degrees. So this will be approximately, this will be 285 Kelvin. Okay. Now let us check the condition 2. So the condition 2 is here, V2. We want this one, pressure P2 is equal to P atmospheric pressure, and the temperature T2 is equal to 35 degrees Celsius. So 35 degrees Celsius, if we add this, so we will get 308 Kelvin. Okay. So we have got the two initial and final condition. Now let us we know that the what is the ideal gas condition. So the ideal gas condition is that PV is equal to nRT. So now we can also write here nR, number of moles, everything will remain same. What we will change, since mass is not changing, so the pressure, volume by temperature will change. So nR will remain constant. So if nR will remain constant, so we can write here P1 V1 divided by T1 is equal to P2 V2 by T2. Now our target is to find volume V2. So from here we can find volume V2 is equal to P1 B1 into T2 divided by T1 into P2. Now the thing is that we don't have a value of a P2. No, sorry, P1. Since P2 is equal to 1 atmospheric pressure, so this is equal to 1.01 into 10 to the power 5 Newton per meter square or Pascal, we can say that. Now the pressure P1, so our target is to find pressure P1. So pressure P1 is equal to 1.01 into 10 to the power 5 pascals plus rho gh. Rho is what? Rho is the density of the water. So this is 1000 into g is 9.8 into height is 40. So when we multiply it, when we find it, so we will get the value approximately equal to 4.93 into 10 to the power 5 Pascal. So we have got now the value of a P1. Now we can easily find out the value of P2. So P2 is equal to P1. So put the value of P1. So this will be 4.93 into 10 to the power 5 into volume V1. V1. So let us consider it in a CC only, because we will, if we put the values in a CC, volume in a CC, so we will also get the result in CC. So let us put here 1 centimeter cube, because V1 is 1 centimeter cube, and the temperature. So the temperature is T2. T2 temperature is how much? T2 temperature is 308 divided by T1 is 285 into P1 is how much? P1 is how much? Not P1, it is P2. P2 is how much? It is 1.01 into 10 to the power 5. Now it is our calculation is required. So if we do the calculation, if we do each and every calculation, so our volume V2 will be approximately equal to 5.3 cubic centimeter. So I hope this was the required result for us. So you will get the proper answer from here, and I hope you have understood this question. Okay. Now let us go for next question, that is 12.6. 12.6. We need to study the question. The question they are asking that is to estimate the total number of air molecules inclusive of oxygen, nitrogen and water vapor and other constituent in a room of a capacity 25 meter cube at a temperature of 27 degrees Celsius and 1 atmospheric pressure. Number of air molecules. So number of air molecules, before that we need to find the number of moles only, okay? As we know that PV is equal to number of moles into R into T. So from here we can find number of moles as PV divided by RT. Now if we got the number of moles, then only we will able to find the number of molecules. So how you will find the number of moles? So pressure they have given, pressure is how much? Pressure is 1 atmospheric pressure. So pressure is 1 atmospheric pressure. So this is 1.01 into 10 to the power 5. So we can put here the value of 1.01 into 10 to the power 5. Now the volume is how much? So 25 meter cube. So it is already in standard one. divided by R is 8.314 into temperature is 27. So temperature is 27 degrees Celsius. It means 300 Kelvin. So put the value here 300 Kelvin. So if we get the 300 Kelvin as a volume, if we get the 300 as a volume, then only we can get the values. Now see, we have got the number of moles. Now our target is to find the total number of molecules. As we know that the formula, that number of molecule is equal to number of moles into Avogadro number. So this is very famous formula. So we have to put the number of moles. So we need to put number of moles as 1.01 into 10 to the power 5 into 25 divided by 8.314 into 300 into 6.023 into 10 to the power 23. When we multiply these things, so we will approximately get values approximately equal to 6.097 into 10 to the power 26, 10 to the power 10 to the power 26 number of molecules. I hope you have understood this. So this is our required result. Okay. So I hope you have understood this, and this is our required result. So this is the amount of number of molecules of the air molecules are present inside the room. I hope you have understood now. Now let us go for a question number 12.7. Now 12.7, question number 12.7. Let us read the question first. Estimate the average thermal energy of the helium atom in a room temperature, that is 27 degrees Celsius, the temperature on the surface of the sun, that is 6000 Kelvin, and the temperature of a 10 million Kelvin, the typical core temperature of the stars we want. Okay. Now we know that what is the thermal energy in formula for the thermal energy. So the basic formula for the thermal energy, E is equal to F again. E is equal to F by 2 into K into T, where K is your Boltzmann constant and T is the temperature. Now what is F? So F for helium, since it is a monoatomic, so the number of F is for monoatomic gas is 3. So if we know, we can understood that F for helium is 3. So the energy we will have, energy is equal to 3 by 2 into Boltzmann constant. So the value of Boltzmann constant K is equal to 1.38 into 10 to the power minus 23. So we have to put here 1.38 into 10 to the power minus 23 into the temperature. So temperature we have a 27 degrees Celsius. So for the case 1, if we talk about the case 1, so the temperature is 27 degrees Celsius. So this is equal to 300 Kelvin. So we have to multiply it by 300. So when we multiply it by 300, so our value will become 6.21 into 10 to the power minus 23 joule. So this amount of energy we have. Now let us do for a case 2. Case 2, it is case 2. It is your, we have to find the energy at the surface of the sun. So energy for having a temperature at the at 6000 Kelvin. Okay. So if you want this temperature, so how you will do this same formula? We have to apply E is equal to 3 by 2. Why 3 by 2? Because 3 same gas is there into 1.38 into 10 to the power minus 23 into 6000. In place of temperature 300 Kelvin, we have to put here 6000. So when we do this, our result will be, it will be approximately 20 times this one. So our result will be, let us calculate it. The result will be approximately equal to, just you guess it. So this will be approximately equal to 1.24 into 10 to the power minus 19 joule. I hope you have understood this, right? Now we will go for third one. So the for third one, the temperature of a 10 million Kelvin. So the temperature of 10 million. So 10 million means 10 into 10 to the power 6. So the energy we have is equal to 3 by 2 into 1.38 into 10 to the power minus 23 into 10 to the power 7. So if we will do this, so our answer will be approximately equal to 2.07 into 10 to the power minus 16 joule. So this amount of energy we'll have. Okay. So I hope you have understood this. So this is very simple to understand this question. So let us go for next question. Next question is all about let us read the question. Three vessels of equally capacity have gases at the same temperature and pressure. The first vessel contain neon, that is monoatomic. Second contain chlorine, that is diatomic, and the third contain uranium hexafluoride, that is polyatomic. Do the vessel contain equal number of respective molecules? Is the root mean square value of the speed of the molecules? Do the vessel contain the equal number of respective molecules? And is the root mean square speed of the molecules the same in the three cases? So let us go for this. So there are three vessels are there. This is, and all are equal capacity. That is volume will remain same. Okay. Do the vessel contain equal number of respective molecules? So if we see here, if we assume, if we assume, if we assume ideal gas, if we assume the ideal gas, then what will happen? Let us consider PV is equal to N into R into T. So the number of mole will be equal to PV by RT. So R is already constant. If pressure, volume, and temperature of all the three gases are same, so definitely number of moles will be same. Okay. If this, that is pressure, volume, and temperature will be same, then N will be same. and if n is same, then number of molecules will be same. Number of molecule will be same, and that is equal to Na, that is Avogadro number, and this is equal to 6.023 into 10 to the power 23. So I hope you have understood now. Now, in the examiner or the question, they want that you should assume it as an ideal gas. So the number of molecules, that is, it will be remain same for all the three cases. Okay. Now the case two is that is the root mean square speed of the molecules in of the molecules is the same for in all the three cases. If not, then which is the largest RMS? So we know that the velocity RMS is equal to root under T into R into T by M. See, all the three entity, 3RT will remain same for all the gas. This above part is this will remain constant for all gas. Okay, but this will change. Okay, so M is if PRMS is inversely proportional to the root of the molecular mass. So which has the VRMS largest? So the VRMS will be largest. VRMS here VRMS is largest for minimum molecular mass. Minimum molecular mass. So from the above case, neon has the minimum molecular mass. So the mass for neon is minimum. After that, chlorine mass, and after that, mass of uranium hexafluoride is the highest one. So VRMS is highest for neon. So this, I hope you have understood this. So our required result, this one is our required result. So we have got this result. So the molecule will be same. We have got this result, that constant for all, but VRMS will be changed, and this is your third result. Okay, hope you have understood this. Now let us do the question number 9. Question number 9, we need to understand at what temperature is the root mean square speed of an atom in an argon gas cylinder is equal to the RMS speed of the helium gas atom at minus 20 degrees Celsius. Atomic mass of the argon is given as. See here, there are two gases, that is argon, and there is another gas that is known as helium. And the argon, at what temperature the root mean square speed of an atom in an argon gas? So the temperature of the argon they are asking, and they are also saying that the helium has a temperature of has the temperature of minus 20 degrees Celsius, and this is equal to 253 Kelvin. 253 Kelvin. The molecular mass of the argon is equal to 39.9, and molecular mass of the helium is equal to 4u. It is 4. Okay. So molecular mass they have given. They are telling that at what temperature of the argon, both Vrms of the argon will be equal to Vrms of the helium. So we need to equate both the things. What is so? Let us equate it. Since Vrms is equal to root under 3 kT by m. So here 3k will remain constant. So what will happen? T by m ratio should be equal. T by m ratio should be equal so that Vrms will be equal. So let us consider T by m for argon is equal to T by m for helium. So temperature for the argon we don't know. Mass for the molecular mass for the argon is 39.9. Temperature for the helium is 253, and the molecular mass of the helium is 4. So finally temperature of the argon we are getting as 253 into 39.9 divided by 4. So if we do this, so our value will be approximately equal to, see, this is 39.49 means we can consider this as a 40. So you will directly get 2530 Kelvin as a temperature of argon. So our desired result is temperature for argon is 2530. Okay, I hope you have understood this. Now let us do question number 12.10. Before that, we need to understand what they are asking. Estimate the mean free path and collision frequency of a nitrogen molecule in a cylinder containing nitrogen of 2 atmospheric pressure, 2 atmospheric pressure, and temperature of 17 degrees Celsius. Okay. Take the radius of the nitrogen molecules to be roughly approximately 1 angstrom. So the diameter will be 2, it may be. Now, first of all, we go for a first question. The first question is estimate mean free path. So the formula for mean free path, that is lambda m, is equal to 1 by root 2 into pi into n star into d square. D is equal to diameter. N star is particle density. Basically, star, if you want to find n star, so this will be equal to total number of particle divided by volume. So this is particle density. And the temperature is given as temperature they have given as 17 degrees Celsius. So this will be 273 plus 17. So this will be 219 Kelvin. Now before that we need to understand that how we will find out n star. So as we know that PV is equal to n T. Okay. We have also one formula, PV is equal to, in place of N, we can write here N, number of molecular density, N into K into T. We actually want N by V. So from here, N by V is equal to P by KT, where N by V is equal to N star. So N star is not a number of moles. Here N star is molecular particle density. So we can find here from particle density, how we will find particle density. So just put the value, so we will get the particle density. Now our target is to find the lambda m only. So lambda m will be equal to 1 by particle density. So n star can be written as P by KT. So above it will be P into KT divided by root under 2 into pi into P into D square. So now we have to put the values. So K means what? 1.38 into 10 to the power minus 23 into temperature is 290, and root 2 has a value 1.41 into pi is 3.14 into pressure. So the pressure is how much? So the pressure is approximately equal to pressure is 2 atmospheric pressure. So we can put here 2 into 1.01 into 10 to the power 5 into d square. So d is the diameter. So diameter is, since radius is given as 1 angstrom, so the diameter will be, it will be approximately 2 times. So this will be 2 into 10 to the power minus 10 meter. So finally we will get, if we will do the calculation, so we will get the value as 1.11 into 10 to the power minus 7 meter. So this is the mean free path values. So I hope you have understood this. Okay. Now let us go for a question. Second part question. Now in second part, see here, they want collision frequency of the nitrogen molecule. So number of times that it collides in a 1 second is known as collision frequency. Okay, collision frequency means in 1 second it move. Collision frequency means collision frequency. For example, any nitrogen gas is moving like this, like this, like this, like this, like this. So how many times it collide within 1 second, we need to find out. So collision frequency, that is basically can be found out by the velocity Vm by lambda m. Why Vm by lambda m? Because we are taking time as 1 second. So within 1 second, how many times it collides? Okay. The average mean path is lambda m. So lambda m is the distance travel, and this is the velocity. So from here we can find up collision frequency. So the collision frequency, the Vm. So what is the value of Vm? Vm here, Vm is what? Average velocity. Average velocity here, not a RMS velocity. So average velocity is, the value of average velocity is, it is 8 into r into t by pi into m. So these are the formulas for the average velocity. So if you put the value of these things, so we will have 8 into 8.314 into temperature. So temperature is 290 divided by pi. This is equal to 3.14 into m. So m is mass. So mass should be 28 into kg, because we are taking all the things in a standard one. So collision frequency will be approximately equal to 4.22 into 10 to the power 9 hertz. Why? Because it is occurring per second. So this collision frequency is hertz. Okay. So I hope you have understood this. So this question has been done. This question has been done. Now take the radius of a nitrogen molecule to be roughly. Now compare the collision time with the time of the molecules move freely between two successive collisions. So we have to find the ratio. See, what ratio? Let us consider. Let us consider there is a movement. There is a movement, Brownian movement. The molecules is moving like this. It is also colliding like this, colliding like this, colliding like this, colliding like this. So we are talking about initial and final. But before that, how many times it has been collide in intermediate? So five times it collide. Okay. So initial to final collision, but initial to final collision has collide to five times. So the time required for each five times collision is how much collision time, and the time required is for initial and final collision is collision time. So we have to compare. We have to compare basically what is the time. So how we will compare it? So we have to compare it by doing like this. So intercollision time. So for this we have to write here intercollision time. Intercollision time. So that is ICT is equal to lambda m by Vm, because we are talking about average velocity. Then only we will get the intercollision time. So we will get intercollision time as intercollision time as lambda m by Vm. So we have got lambda m by Vm. So we have just found out that Vm by lambda m is like this. So lambda m by Vm will be equal to 1 by 4.22 into 10 to the power 9. So we have got intercollision time. Now we have we need to find collision time. So collision time means what? Initial and final. Initial and final time we have to find out. So how you will find collision time? So we know that collision frequency is how much? Here we have to find first of all collision frequency, and that after that collision time. So collision time, how you will find the collision time? See, collision time is what? See, they are telling us that molecules are approaching from here. If you read this question, so they told that the time when it collides, so what will happen? It will compressed, so the size will become in such a way that its radius will reduce. Earlier, the radius distance between the center was 2r. Again, its center become r, and after that, it again go in such a way that its distance between the center become 2r. So the total distance travel is how much? Total distance is equal to 2r, and velocity will be taken as v average only. So the collision time can be found out by 2r divided by velocity vm. 2r means 2 into radius is 1 into 10 to the power minus 10 divided by velocity, mean velocity. So mean velocity we have already found out, it is equal to 468 meter per second. So when we find out the velocity of collision time, so collision time we will get as 4.7 into 10 to the power minus 2 second. Now we need to compare the intercollision time and collision time. So it means that we have to find the ratio. So we have to find the ratio. So how you will find the ratio? So this will be ICT divided by CT. So ICT is 1 by 4.22 into 10 to the power 9 divided by collision time is how much? So collision time is 4.2 is 7 into 10 to the power minus 2 second. When we calculate this, so we will get 550 times. So intercollision times is the ratio will become 550 times. It is minus 12. See here, it is minus 12, not a minus 2. It will be minus 12 only. Okay. So this is what our required answer is. I hope you have understood this. Thank you for watching my video. If you have a doubt, then you can ask me. And I hope you have understood these things. It means that intercollision time. So 550 times it will collide when there will be one collision time. So intercollision time will be 550 times. When one molecules will go from one side to another collision, so what will happen in between? There will be a 550 collision will be happen. So this is the thing they are asking. I hope you have understood this. Thank you for watching my video. Hope I will meet again for in the next video. Thank you.